Hello and welcome to class number 6. Today we cover something called the second fundamental theorem of calculus. Hopefully you're making progress on project number 2, which is due in 2 classes. And quiz number 2 is due next class. That one you have several copies of at the very beginning of our packet. The answer key is also at the beginning of our packet. So take that one as many times as you need to until you get 100. If you need more than the number of copies in the packet, go print them from Moodle. So let's jump to the packet right around page 56, daily summary. In this class, we meet the area accumulation function and the fundamental theorem of calculus part 2. In the interest of full disclosure, the FTC2 is a funny and contrived theorem. It's interesting not for its practical application, but for the surprising connection it illustrates. Number 1, first let's review. On left is a derivative function, little f of t. Using techniques we have learned, sketch an antiderivative, capital F of t, on the right. This is a rough sketch. We are only thinking about increasing, decreasing, and concavity, and we will assume that capital F of -4 is 0. So let's make sure we're okay with the difference between lowercase f and capital F. So lowercase f is this function right here, and capital F is the one that we are trying to graph ultimately over here. And it says that capital F is an antiderivative of little f, which means if you take the derivative of capital F, you get little f. So I'm just going to be thinking about capital F from this point forward on this problem. On the right is going to be the original capital F function. On the left, already graphed for us, is its derivative. So let's start by thinking about where capital F prime is positive and where it's negative. So from here to here, capital F prime is positive. Capital F prime is positive. And if capital F prime is positive, that means that f is an increasing function. Likewise, from here to here, capital F prime is negative, below the x-axis. And therefore, capital F is a decreasing function on that same interval. And then finally, here to here, capital F prime is positive again, which means that capital F is increasing. So we've got some stuff about capital F being increasing and decreasing. Let's go ahead and draw a very rough sketch on the right-hand graph. In this problem, we're told to assume that f of -4 is 0. So that's going to give us a starting point. F of -4 is 0 is that point right there. And then we're going to draw something which is increasing until we get to around -2.2, decreasing until we get to around +2.2, and then increasing the rest of the way. So it's increasing until 2.2. So let's graph over here something that is increasing until, sorry, I said 2.2, I meant -2.2. So something like that. And I'm stopping right there at around -2.2. And then it needs to be decreasing until +2.2. So we're going to draw something decreasing until around there. And then it's supposed to be increasing the rest of the way, something like that. So that is a very rough sketch of capital F. So now we're going to fine tune our sketch by thinking about where capital F is concave up and where capital F is concave down. So I've got one more highlighter here. Let's see if we can use it. So if we take a look at capital F prime, the left-hand graph from here, let's see. Yellow and blue make green. That's not so good. Let's just do red. If we look at capital F prime from here all the way over to here, on that interval, capital F prime, the graph we are looking at right here, is decreasing. And that means something very specific about capital F. It means that capital F is concave down. So capital F is going to be concave down everywhere to the left of the y-axis there. And if we look at capital F prime from here onwards, we notice that capital F prime is increasing. And therefore, capital F is concave up. So let's fine tune our graph on the right-hand side. We just got information about capital F. It's concave down in the beginning until we get to the y-axis and then concave up. So I'm just going to try to follow this purple up, down, up thing, but with the sort of fine-tuning we just discovered about concavity. So we need to be concave down in the beginning. So here to here, concave down. And it continues to be concave down until we get to the axis. And now it needs to be concave up, but still decreasing until we get to the bottom here. And then it needs to be concave up and increasing the rest of the way. So purple was our first attempt. Orange is our much more fine-tuned attempt, just thinking about increasing, decreasing, and concavity. Okay, moving on to number 2. Next, we will create a table of values for what we call the cumulative area function, little c of x. This function is defined in the following way. C of -3, so I'm defining a brand new function c. C of -3 is the area between the above left curve and the x-axis from -4 to -3. The area between -4 and -3. So that's this space here, following the curve, something like that. So, oh, sorry, no, that's not that at all. I should have stopped at -3. So we'll wait for that thing to fade. There it goes. So the area that we were talking about should have been right there. The area in that space is our definition for C of -3. And if we keep going here, now I'm over here, C of -2 is the area between the above left curve and the x-axis from -4 to -2. So let's look at that one. So C of -2 goes all the way to here. So it's the area, I guess that piece is positive, and then there's a little piece here down that's negative, but it's the combined net area of those two things. Whatever that number is, that's what we're defining C of -2 to be. And I'll just point out that the thing that was held constant both times is the -4. So it's always going to be from x equals -4 to the number in the parentheses, from x equals -4 to the number in the parentheses. And it's just the signed area. And so here it is written in our definite integral form. C of -3 is just the area from -4 to -3 up the above left curve. C of -2, again, always -4 at the bottom. And this one just goes up to -2. And in general, C of x, we'll just plop that x right up there, and we start our area accumulation at t equals -4. Okay, so let's fill in the following table. Approximate each area by using a single trapezoid or by using 2 triangles if the graph crosses the x-axis. Once your table agrees on the value of C of -4 and C of -3, feel free to divvy up the work involved in estimating the remaining areas. Once you filled in the whole table, check your final entry. It should be C of 4 is approximately equal to 3. So let's do a few of these together here. All right, so the first one that we want is right here. It's C of -4. So let's just write the definition. So according to the definition, C of -4, I'll put this a little bit lower. C of -4 is the integral from -4 up to, I'll leave a blank up there at the top, and then it's little f of t dt. And the number that goes up at the top is always the number that's in the parentheses. So in this case, it happens to be -4. The number at the bottom is always -4. And this integral is easy, right? Because integrating from -4 to -4 means you sweep out no area. So this one is equal to 0. Okay, but let's try the next one. So now we're working here. And I'm going to write the definition for C of -3. It's the integral always from -4 up to the number in the parentheses, the function on the left. So we're interested in approximating that area. So now we're just going to do some estimating looking at this graph on the left. So I want the area from here over to -3 and then back up and then up to the curve. And so if you happen to know the formula for the area of a trapezoid, you use it here. I think most of you are going to cut this thing into a rectangle and a roughly triangle. So the area of that rectangle, careful, it looks like it's just 2 boxes, but the vertical here, the scale is 2, not 1. So the area of this rectangle is actually 4. And then the area of this triangle, so we're doing half the base times the height. So half of the base here is 1, but the height here looks like it's from 4 to 10, so that's a 6. So 1 times 6 is 6, and then half of that is 3. So the area of that triangle up there is 3, and the triangle does a decent job of approximating the area under that red curve. So the total area there is 7. It is all positive, and that's what we're putting in here. We're just putting the number 7 because what we were after was this integral, and we know that that integral just represents the signed area from -4 to -3. Okay, moving on to -2. Let's do that one now. Okay, so looking at -2, I'm gonna see, let's use blue here. So I've already calculated the area from -4 to -3. That was an area of 7. And now we're gonna look at this thing here, roughly triangular, and then this thing here, also roughly triangular. And we're gonna calculate the net area. The thing above the x-axis is positive and the thing below is negative. So let's work out these areas. So the area of this one, again, assuming it's a triangle, half the base times the height. So the height is maybe 4, right? Like coming up to here. So maybe the height there is 4, and then the base, I don't know, like 3/4, something like that. Let's try that one. So half of the height times the base, 3/4. Maybe that's a good approximation for the area of this triangle. So I think if we do that, we get 1.5. And then we've got the little triangle down below, this one. So let's calculate that area. So it looks like maybe the height of that one is around, remember again, look at the scale. So maybe that's around 1.5. And the base is the other quarter that we didn't get from the first triangle. So half of the base times the height. Height, I think I said, was around 1.5. So 3/2. Oh, man. 3/2, something like that. And so if we smush all that together, what is that? 3/16. So let's get that as a decimal real quick. 3 divided by 16. Let's just call it 0.2. Come on. So that's right around 0.2. Except it's below the x-axis. That little triangle counts as a -0.2. So then the net area we gain there is the 1.5 positive, and then subtract the 0.2 negative that's below the x-axis. So it looks like it's a gain of around 1.3. But remember, we were looking for the area from -4 to -2. And we already had a 7. And now we just gained another 1.3. So that means altogether 8.3 is our answer. So 8.3 roughly goes right there. And so this is a good time for you to pause the video and go ahead and see if you can fill in the rest of this table. Your answers are going to be approximations just like mine are. So I'm going to do my estimating, you're going to do your estimating. Pause the video here, come back when you are done, and check your estimated answers against mine. Okay, so hopefully you got your table filled in. I put my numbers up there in green. They should be close to, but slightly different from the numbers you have. My approximation when I first made this problem was C of 4, supposed to be around 3. I ended up with 2.6. Again, there's a pretty wide range of acceptable answers here. So there's our accumulation function filled in table-wise. And on the next page, you're going to jump in with the group activities. It says pick up where you left off in the demo and sketch a graph of C of X at the right. That means just plotting all of these points here. Just so plot these points on your graph on the next page. You might want to pause the video here so that you can look at the screen and maybe just copy my numbers or recopy your table on the next page if you wish. And then work through the activities. It's going to take a bunch of time to get through the activities, so maybe give yourself half an hour or 45 minutes or something, and then come back for a short demo at the end of this video. So go ahead and pause the video here, and then come back when you're finished with the first round of activities so that we can do demo number 2 together. Okay, so here we are in demo number 2 with question 1. Find the values of these expressions by using the shortcut, but know that each of these requires one step more than the previous problem did. So part A says find the derivative with respect to x of the integral from x to 0 of b over cosine b db. So this looks an awful lot like the form of the fundamental theorem part 2. The problem is that these two things are in the wrong order. The fundamental theorem part 2 requires the variable to be upstairs and any constant at all to be at the bottom, and that's the opposite of what we have here. So let's go ahead and do what we know we should do in order to flip the limits of integration, and that's to make the integral a negative of what it once was. So I'm copying everything, except when I flip the limits of integration, I just make the whole thing negative. So the integral is really negative, the integral from 0 to x. And we know that that negative sign right there is a constant multiplier, and it's really a -1 times. And so that -1 can come outside of the derivative. That's a property of derivatives. So I'll pull the negative outside, and I'll copy everything else. And now this looks exactly like the fundamental theorem of calculus does. I'm copying the negative sign from the front, and then the rest of this, the derivative of the integral from 0 to x, just means change the b's in the integrand to x's. So our final answer is just the negative in the front, oops, change the b's to x's. Negative x over cosine x, and that's it. So the only work involved here was swapping the limits of integration so that it looked exactly like the form of the fundamental theorem part 2. Okay, B. Derivative of the integral from 1 to sine of x of 1 minus t squared dt. Okay, so the part that's new here is that instead of being plain old x up there, it's actually a more complicated function of x. Let's go ahead and use the fundamental theorem naively, pretending it's not complicated, it's not sine of x, but if it was just x up there, then our answer would be 1 minus x squared. Except it isn't just x, so it's really 1 minus whatever is up there playing the role of x squared. So it appears that our answer should just be 1 minus sine of x, that quantity, squared. But that's not the complete answer. We are doing a derivative, and we applied the rule as if the thing were x. But if the thing is any more complicated than x, then we have a rule that allows you to take a derivative when the stuff isn't just x, and that's the chain rule. And so the chain rule would say, do your normal derivative rule, which we have just done by replacing the t with sine of x, that's the stuff, the sine of x. But then at the end, multiply the whole thing, your regular derivative rule, by the derivative of the stuff. And so we just put right over here the derivative of sine of x, which is cosine of x. So that's it. 1 minus sine of x squared, the whole thing times cosine of x. Let's take a look at part C. It's the derivative of the integral from 21 to 5x squared minus 3x of w plus ln of w dw. So this is exactly the same technique. We change the w's to the stuff. There's the stuff right up there. So both of those w's become 5x squared minus 3x. So that's the w plus ln of the same stuff, 5x squared minus 3x. But then the chain rule says if you're doing anything other than just plain x up here, you have to multiply by its derivative. And so in this case, the derivative of that stuff is 10x minus 3. But that derivative is really one thing, so it needs parentheses. So that's our final answer right there. Okay, once you're feeling good about demo number 2, move on to activities number 2, which should be on the next page. Actually, I just saw the next page is the even more practice section. So if you have time and mojo, then keep on practicing with these problems. Otherwise, go ahead and jump in and work on the homework. See you next class.